Let us discuss a very beautiful construction problem. I'm referring to article number 9 of our textbook, College Geometry. We are asked to construct a square so that each side or the side produced shall pass through a given point. Well, let us consider first four given points, A, B, C, D, and these are 4 points in a two-dimensional system, and since they are independent, A, B, and C and D can be located anywhere in the plane. But is there a square that will pass through them? Let's consider yes, there is always a square that will pass through them, and that's what it is, okay? So that's what it is. However, is this the only solution that we've got? Well, I've got, look at this one. So in the first one, A, B, C, and D are all on the sides of the square, but it's not possible that it's always like this one. It's possible that A is outside of it, but what that means is the fact that it is on the produced side, on the extension side of this particular square. And as a matter of fact, I can make all of them be located outside that one, okay? And that's what it is. And so in this particular solution, A, B, C, and D, these 4 points are located on the extension side of the square, or the side produced of the square. Very cute. So here I extended the lines, the sides of the square, so that we visualize the sides of it. This side contains C. This particular side contains point D, and this particular side contains A, and this contains B. Or it can be here, or D can be here, C can be outside or inside, and B is located here. Okay? Still, is that the only thing that we've got? Do we only have one solution? Well, we'll see. Now we have two squares in it. Okay, two squares, all of them pass through points A, B, C, and D. So this passes through C, this passes through B, and this passes through A, and finally this one passes through point D. Now for the red square, this side contains C, this side contains B, this side contains A, and this side contains D. So indeed, there are two solutions. And just to clarify, here are the sides of those squares, and we can now see one more time that this side contains C, this side contains A, this side contains C, and D is contained here. And the same is true for the red square. Well, there are four solutions. Wow! Okay, since there are so many of them, we can slow down so you notice, okay, wherever I can dislocate A, B, C, and D, and still all of them seems to be a correct solution. So let's find this side, okay? So let us consider the sides of the blue square and confirm that for this particular square, this side contains A, this side contains B, this side contains C, and this side contains D. For the bigger square, blue square, it contains D, this one contains C, this one contains A, and this one contains B. Clever! Wow! Now, for the black squares, let us extend the sides of it. And these are the sides of it. For this particular square, it contains C. Let me exaggerate. There we go. This side contains C. This side contains B, D. This one contains B, and this one contains A. And the same is true for the other big squares, okay? So, I think we are ready to discuss how we are going to attempt to solve this one. But it seems easy, but not really that easy. So, first, we will consider a very useful problem. Sometimes we encounter this once in a while in a math competition, but it's a variation of this particular problem. So, and that is, if we are given square A, B, C, and D, and we have two segments on the square such that point E is on AB, point F is on CB, point G is on CD, and H is on AD. If the segments are so constructed so that these two segments are perpendicular, then it must be true that GE and FH are congruent to each other. If you notice, if I drag A, B, and C, okay, GE and HF will always be congruent or equal in value to each other, okay? However, I can also drag a point F. If I drag point F, you notice that the values of GE, HF change, but their measurements are equal to each other. Therefore, they must be congruent to each other. So to prove that, okay, let us construct lines perpendicular to the sides passing through point G or point F, okay? Or it could be the other way around. So I want to construct either the perpendicular lines or the parallel lines. And that's what we've got. Okay, and with that, we'll see. Okay, which angles? Let us chase angles. Okay, well, here it is. With respect to this angle 5 here, 2 and 4 are complementary. And with respect to angle 1, angle 3 and angle 4 are also complementary. Therefore, 2 and 3 are both complements of angle 4. That tells us something. And that constitutes the proof of our discussion. Here it is. Okay, so we constructed lines that are perpendicular or parallel to the sides of the square through points G and H. Okay, so through G, construct a line perpendicular to the side or parallel to this side. Through H, construct a line perpendicular to this side or parallel to the sides. No matter what, this segment is congruent to the two other segments, and HI is congruent to AB and to CD. Hence, HI must be congruent to GJ. That's the first thing that we are going to consider. Next, I already mentioned that 2 and 4 are complementary angles, 3 and 4 are complementary angles. Therefore, angle 2 and angle 3 must be congruent to each other. 2 congruent to 3, let us hide now those ones, okay? Let us show the blue angles and the blue triangles, blue triangle and red triangle. This is congruent to this. This is 90 degrees, and the sides are congruent to each other. Therefore, the two triangles must be congruent to each other. And that leaves us with the fact that the hypotenuse HF and hypotenuse GE are indeed congruent to each other. Wow. Okay, now that we have proved it, what does it have to do with the problem? Well, we'll see. Okay, again, we want to construct it. So here are the 4 given points. And the big idea we got from that problem was the fact that DF and AC are perpendicular to each other. But how do we do that from given points A, B, and C? Well, what we can do is, okay, that's just a given problem. So let's start again one more time. So I would like to construct, because of the fact that we had this one perpendicular to this, so I will consider one point to be perpendicular to 2 segments in here. So out of these 4 points, why don't I construct A and C and construct a line perpendicular to that one passing through point D? That's just one of those, and then I can change the stuff. So let us consider points A and C and construct segment AC and a line perpendicular to C. Oh, this must be passing through a line T. T must pass through point D. Okay, so where's that? That is step number 1. So again, coming from point D, construct line T that's perpendicular to segment AC. Easy. Now, from point D, I would like to construct 2 points, F and F prime. Okay, so that DF is congruent to AC. Keep in mind, I want to imitate these two segments here that are perpendicular to each other. So I am now in step 2. I would like to do that one. So here it is. I would like to construct F prime and point F. We know, I constructed it so that DF is congruent to AC and also DF prime is congruent to AC. Well, from there, I think I can now construct a square. Everything is so procedural now. I want to construct a line BF. That is step 3. There you go. And then construct AF perpendicular to BF and CF perpendicular to BF also. So from this line, construct 2 lines perpendicular to it coming from A and coming from C. That is step number 4. That's what it is. I can locate it. So let's see that. Okay, there you go. I want it to be a little bit twisted. Okay, that's what you've got. Now, since this must be the length of the sides of my square, so I need to locate 1 point here and 1 point here so that I have the square. And definitely that will pass through point T. So that is now locate point P and point S on AQ and CR respectively so that PQ equals QR equals RS. That is step number 5. And that's what it is. Now I'm able to locate 4 points P, Q, R, S, and all I need to do is to construct them. And that's what it is. Okay? Now, with point F prime, I'll just repeat the procedure. But it might be a little bit confusing, so let me hide first a couple of stuff. There you go. And what I want to do is now I want to hide this one and hide this one, and that's what it is. Okay, you know what, let me just hide all of them for now so that we can focus on the procedure. A while ago, sorry, I need to keep points A, B, C, and D. There you go. Okay, so A, B, C, and D are given, so I need to focus on this. But this time, instead of focusing on F, I will focus on the other point, BF. Okay, and that is now BF. I want to construct BF, so you notice I will just repeat the procedure. It's like iteration, and that's the beauty about doing it in computer geometry, okay? Because, you know, I can focus on one aspect, one task at a time. So now I'm doing this, but this time using point F. So construct line BF, and that's this one. And then using the same procedure, but this time I will now use AQF and CRF, CR prime. Okay, so what would that be? Maybe let's do step 4. There you go. Okay, let's do it a little bit far. There you go. And finally, I will locate 2 more points, P prime and S prime. And I have these points here, and then that's where square PQRS is, okay? But that is symmetrical. Let me show one more time the 2 points. So the first one is bigger one, the second one is a small one, but it makes use of the same principle that AC is perpendicular to DF or DF prime. That's so beautiful. Now let me hide this. And I can now hide this one. Okay, and hide this. Again, let's review the procedure. What we have done was we focus on DF perpendicular to AC, and the other one is df prime also congruent to df also. And with df, I constructed a big square, and with df prime, I constructed a square p prime, q prime, s prime, s prime. They are symmetrical, okay, in nature, and the solutions were constructed in a very similar manner, okay? Now, if I construct, what we did was to construct this, I constructed a line from point D that's perpendicular to AC, and there were two solutions. This time, if I construct from point D that's perpendicular to AB this time, and to, okay, so the first one is to AB and to BC, then I will have two sets of two squares. That makes it four more squares, and hence we have a total of 6 solutions. That seems to be a little bit uh, confusing. So what we can do is to show it to you. Here it is. So here are the 4 given squares. And let's consider the 2 squares, 2 more squares, the blue squares, and the green squares. Okay, so 2 red squares, 2 blue squares, one is almost inside that one, and then 2 green squares, okay? That is the thing that we've got. There you go. Wow, so cute indeed. Okay, let's check. This one passes through A, this passes through C, this one passes through B, and this passes through D. That's for this square. For this red big square, this passes through C, passes through D, passes through B, and passes through A. Wow. For this, okay, let's consider this small blue square. This one passes through D. This one passes through, where is that one? This one passes through B. This one passes through A. Okay, if it's not so clear, let's construct the line. Construct the line. Indeed, it passes through D. Construct this line. Construct line. Oops, it passes through C. Construct this line. Oh, I think it will pass through A. Let's see. Yes, indeed. And finally, this one will pass through B. Yes, so indeed, all these 4 squares, 6 squares rather, pass through points A, B, C, and D. Very beautiful indeed. Very simple, but it's nerve-wracking. Cute, huh? Thank you very much. See you in the next problem. Bye-bye.